All right, in this last part of my lecture, I want to talk about applications of quantum dynamics. Um, but first, let me outline to you what our goal is and how we approach our everyday research. So the goal is to develop quantum algorithms and use them on hardware, of course, in order to outperform classical computers and classical algorithms, of course. Now, for this, we proceed in multiple steps. And the first one, and possibly the most important, is to identify hard problems. What do I mean by this? Obviously, some problems might be easy enough to solve very well on classical machines using classical algorithms. And it is not clear if quantum computing can have an advantage to solve these problems. So in order to identify problems where this is not the case and where quantum computing could have an advantage and impact over classical algorithms, one has to know the specific field of physics or chemistry or whatever that they're interested in very well, and also has to have a good overview of the classical algorithms used within this field to solve problems, and then use this knowledge to identify where are the limitations of certain classical algorithms and what are problems of interest that this respective community wants to solve, but that they cannot solve due to these limitations of their algorithms. So, for instance, because the system size is too large, or because there's so much entanglement in the system that the algorithm cannot reproduce exactly, but it's necessary to describe a certain phenomenon that you're interested in, and so on. Okay, so that's the very first step, to identify hard problems and to know what is even relevant and what might be good to do on a quantum computer that you cannot do very well classically. Okay. And the second step is, okay, now we know what hard problems are. Can we actually do better on quantum computers? And for this, we need to think about how do we represent this problem in terms of qubits and quantum gates. So can we find a representation that's good, well suited for quantum computing? And also, can we construct algorithms with which we can efficiently extract the information that we want from this problem? So we want to measure a certain thing inside of a certain system. First of all, can we represent the system on our hardware? But then also, can we measure efficiently? So without a ton of measurements, with few measurements, can we extract the information that we're interested in? Okay. These are also two very important questions that are far from obvious for certain problems. And then if you go further than this, you could ask yourself, okay, in which regime can we actually be advantageous using quantum computing? So we want to simulate a certain system of certain size and to a desired accuracy. In which regime of this system size or accuracy does quantum computing actually start to become advantages over classical computing and cutting-edge algorithms in classical computing? And then if you want to go one step further, a question that we also targeted in this paper that might be published soon, hopefully. We also asked which application amongst many applications that that already went through these steps, which of these applications will likely lead to a quantum advantage first, because it might be best representable on quantum hardware with like few qubits, or because it might be easiest to extract relevant information from these systems. Okay, so now that I gave you a bit of an insight into how we do our research, let's go to quantum chemistry. Okay, after this long and enduring algorithm part, maybe this will be a bit refreshing with some more application orientation. Okay, so let me bring back the slide that I showed you in the very beginning to motivate why we need quantum dynamic simulations. I gave you this example of a molecule or some chemical compound on which you do a spectroscopy experiment. So you probe it with a laser pulse, for instance, and then it excites, evolves, and radiates off some light again, which you measure. And through this measurement, you obtain such a spectrum, so such a distribution of different frequencies at different intensity. Okay, and from this you might then extract whatever kind of information. To simulate this, I walked you through all of these steps. So initial state preparation, evolution, and measurement and information extraction in the end. But to actually do this, there's this Hamiltonian here that is the crucial part in this, essentially, right? And so to do this for chemistry, for molecules, for materials, whatever, you need to implement essentially the full quantum mechanical nature of this molecule or chemical compound that you're interested in. And so this Hamiltonian gives you all of this, okay? This is the Hamiltonian of molecules. So this is the molecular Hamiltonian, sorry. And so for some of you that do not have a quantum chemistry background or have gone so deep into quantum mechanics, let me explain to you the constituents of this Hamiltonian, okay? So you might recognize these operators here that are essentially three-dimensional derivatives of your coordinates. And then you also have these two different kinds of coordinates here, okay? These lowercase coordinates represent electrons. These uppercase coordinates represent the nuclei, okay? So think of this naive and not correct picture of atoms by Bohr. So you have some nuclear particles here in your nucleus, right? So protons and neutrons and so on. And then you have, I don't know, let's choose yellow, some electrons flying around here in these different shells, okay? So this is not correct because we know it's actually a probability distribution of electrons, but you still have electrons and nuclei, and these interact with each other and have some motion, and all of this is described by this Hamiltonian, okay? So these first two terms here describe the kinetic energy, so the energy due to motion of the electrons and of the nuclei, okay? So this capital M here is the mass of the nuclei. These terms here represent the potential terms, namely the Coulomb interaction between electrons. So they're electrically charged particles, so they have a Coulomb repulsion. And so this is the electron-electron interaction, okay? Similarly, this is the nuclei-nuclei interaction, because nuclei are also charged particles, so positively charged. So they also have this repulsion. These Z's are the atomic numbers, so the charges of the nuclei. And then in this last term here, you have the interaction between nuclei and electrons, because, I mean, one positively charged, one negatively charged. Of course, you also have an interaction, a Coulomb interaction between them, okay? And then imagine you have a bunch of atoms inside of a molecule. You have many different electrons, many different nuclei, and all of these interact in this fashion, okay? So kinetic terms and potential terms of the Hamiltonian. To describe or to model your system fully quantum mechanical now, you need to consider this Hamiltonian completely. And this is extremely difficult because your wave function will generally depend on both coordinates, right? On the coordinates of all of your electrons and the coordinates of all of your nuclei. So you can already imagine if you have like 50 electrons and 10 nuclei, which is not even a big molecule, you already have 60 different degrees of freedom, which can all be in superposition. And so this exponentially blows up already with very few atoms in your molecule, okay? This description of the wave function. As a little disclaimer, in this I will talk about stationary problems or stationary stationary molecular quantum dynamics, so the time-independent Schrödinger equation, just because it's a bit easier to explain on this. But all of these things, all of these concepts that I'm going to talk about carry over directly to the dynamics, the dynamical problems, okay? Just be aware. So what's usually done in classical simulations to simplify this is the so-called Born-Oppenheimer approximation. And if you have been following this lecture series, Yeva probably told you about it yesterday in the previous lecture. But I will still go through it. Maybe it's also good as a little refresher. So within this approximation, you essentially say, okay, electrons have a much lower mass. They're much lighter than the nuclei. And so their motion is much faster than that of the nuclei, okay? Because they're so much lighter, they can essentially move much more fast than the nuclei. And so what this means is, due to this difference in speed or velocity, the electrons will see the nuclei as fixed. Essentially as their position being constant in space, and vice versa, will the nuclei only see a smeared out field of electrons, so this mean field of electrons, because the electrons simply move so fast that from a nuclear point of view, you cannot distinguish the point anymore, but you only see this mean field of electrons, okay? So a very naive but hopefully intuitive picture. Now, if you do this approximation, you can do another approximation and say, okay, my full molecular wave function is actually factorized into an electronic part, so a wave function part that describes only the electrons, and one that describes only the nuclei, okay? Now you see here, there's still this R in the electron part, but the crucial observation here is that we only take this as a parameter. So it's constant, okay? Because we say, from an electron point of view, the nuclei don't move, but still this has to depend on the electron, on the nuclear coordinates. So there's an interaction with the nuclei, but they are constant and fixed in space, okay? So this R here is just a parameter. If we do this, then we can solve an electronic Schrödinger equation where we neglect this kinetic part of the nuclei first. And if we solve this only for the electronic wave function, then we end up with this eigenvalue problem where the eigenvalues corresponding to these electronic wave functions are these energies dependent again on this R, okay? Because here you see you still have these interaction terms in this electron Hamiltonian, and since they're constant, they are parameters, but this in turn also means that the eigenenergy corresponding to this electronic wave function depends on these coordinates R, okay? So if you then go back and plug this into your, so you plug this in here and you write down the full Hamiltonian again, you apply the full Hamiltonian to this ansatz. And what you find is that first, I mean, there's this electronic part here resulting in this term. So you have this electronic energy dependent on the nuclear coordinates. And then you have the kinetic part, or the kinetic nuclear part applied to your ansatz, okay? And so first of all, this is the kinetic term applied only to your nuclear wave function. But then in principle also you get these mixed terms here, right? Where your kinetic nuclear operator is acting on the electronic and on the nuclear wave function, and also only on the electronic wave function, okay? And now this is the crucial approximation here, because by saying that in the Born-Oppenheimer approximation the nuclei are fixed, this means we neglect these terms entirely, okay? And so what we end up with is the simplified Born-Oppenheimer Hamiltonian, where the nuclei now, or the nuclear wave function is now solved with this simplified Hamiltonian, and the nuclei only see the mean field of electrons through this electronic energy here, okay? Which still depends on the nuclear coordinates. And so this is this great simplification that the Born-Oppenheimer approximation does, and it works really well in a lot of cases, but it also breaks down in cases where, for instance, if you excite your molecule with like really fast laser pulses, the molecule might get excited in such a way that the nuclear motion becomes so rapid that this approximation breaks down. And in fact, these terms here are not small and negligible anymore, but contribute so much energy to your entire system that they cannot be neglected anymore, okay? So if you want to go one step further, you can say, okay, I expand my wave function to some order k in electronic basis functions. This is also still an approximation, and I do the same procedure as, I follow the same procedure as before, okay? I solve this electronic problem first, then I get for each electronic wave function, I get this corresponding energy here. And then I again construct this Born-Oppenheimer approximation, Born-Oppenheimer Hamiltonian, okay? Now, for each electronic excitation that I include in this expansion, I get a different potential term here in the nuclear problem, okay? And this is what we refer to as potential energy surfaces, yeah? So essentially, how you can picture this is you have these potential energy surfaces, which it's a fancy name, but it really just means that the electrons of your molecule are in a different excited state, okay? And this excited state is this potential energy, okay? But think about it like this. Your electrons, depending on the excitation that the electron is in, they interact differently, more strongly or more weakly with the nuclear part, okay? Because they might move differently and they're generally in a different state. And this is represented by these different potential energy surfaces, okay? So here you have this potential generated by the electrons, and you have some nuclear wave packet moving on this potential, okay? Now, depending on the n that you choose here, you can say, okay, the nuclear wave packet is moving on the lowest excited state of the electron, so the lowest potential energy surface, or it can be on an excited state of the electrons, right? And then in particular, if you go beyond the Born-Oppenheimer approximation, so you start including certain couplings here in this Born-Oppenheimer approximation, you can start introducing couplings between these potential energy surfaces, and your wave packets can suddenly jump from one of these energy surfaces to the next, okay? So if you want to do this exactly and you want to account for all of the interactions that are possible in your molecule, right? So all of the different ways that nuclei can excite electrons, or electrons can excite nuclei, and so on, then you need to go one step further. But let me briefly mention in this picture where the nuclear wave packet jumps from one to the other potential energy surface, okay? This essentially means that the motion of the nuclei excites the electrons into a higher excited state, okay? Because this potential energy surface essentially refers to the excitation that the electrons are in, okay? And so it's really, this picture is the nuclear wave packet moving to a different potential energy surface. And so maybe you think, okay, the nuclear wave packet is getting excited or something, but really these potential energy surfaces correspond to the electronic excitation, and so it's more correct to think about this as the nuclei exciting the electrons into a different excited state, okay? So anyway, if we want to do this exact, so we want to have all of the couplings between electrons and nuclei, we have to go one step further, okay? So we can expand this wave function exactly, namely if we include all of the basis functions for the electrons here. Even then we can still solve this electronic problem individually, and then plug this exact expansion into our molecular problem. But now, of course, we also can keep all of these terms back here, so the interaction terms between electrons and nuclei, and this will then give us the full quantum mechanical picture of chemistry, right? Of molecules and materials and so on, where we account for the full interaction between nuclei and electrons as it would have to be done when you want to solve this problem exactly. But as I said, this is extremely difficult and can typically not be done in classical simulations. And so with quantum computers, we hope that we can one day solve this problem, although it will likely not be in the too near future, because even for quantum computing, to implement something like this, you need a lot of gates and a lot of qubits, and so it's not an application for quantum computing that will be solved next year, probably. But how it is envisioned to work in quantum computing is that instead of what you do in classical computing when you want to solve this exactly, you do not have to do this expansion in basis functions, but instead the hope is that you can do this in first quantization directly by encoding this wave function, okay? So you would write or phrase this in terms of a grid encoding of your coordinates, and then you would just initialize a wave packet on this n-dimensional grid with all of these coordinates combined, and then do the evolution under this Hamiltonian, okay? And so what this would also mean is that you would not go through all of these difficulties here, okay? But instead you could use this direct encoding and essentially do the evolution directly using this Hamiltonian, okay? So I hope that I gave you a bit of an overview of what could be interesting in quantum computing for quantum chemistry in the future. And with this, I will go to the last part of this lecture, namely the code example in Qiskit. In this last part of my lecture, I wanted to give a quick code example of showing you how to use some of these algorithms within Qiskit to do time evolution or dynamics. For this, I use an example that was given in this year's IBM Quantum Spring Challenge, namely the tight binding model. It's a very neat model as it's very simple to write down. The Hamiltonian is very easy or very simple, but it has very rich physics, and it's used to describe the electronic band structure in solids, for instance. So the idea is that you have a lattice here, and each lattice side, so these dots here, correspond to an atom, and then you have an electron moving within this lattice or on these lattice sides, okay? And so it cannot go in between the lattice sides, of course, but essentially it can move from side to side, so it can move from one atom to the other. You have two parameters in this model, the epsilons, which is essentially the energy that the electron needs to occupy the respective lattice side, which is numbered also with the lattice side, labeled. And then this J, which is this hopping constant, which is the energy that the electron needs to jump from one side to the next, okay? And this model is described, or yeah, is described by this Hamiltonian, the tight binding Hamiltonian, where this first term here corresponds to these to the electron occupying the respective lattice side or atom side, and you see we can have different epsilons per side. And then the second part is essentially the term corresponding to the hopping between sides. This sum here means that we only sum over next neighbors. So for instance, over these pairs 1 and 2, or and 2 and 3, and 3 and 4, but not over like 1 and 4, for instance, okay? So I and j are always adjacent numbers in this sum. So after this lecture, I think it's obvious that the time evolution of this system is governed by the time-dependent Schrödinger equation with this tight binding Hamiltonian. And the solution of this is looks like so. So you have an initial state acted on by this evolution operator or unitary time evolution operator, and this gives you your state at time t. Okay, so to do this in Qiskit, I mean, before I imported a bunch of packages, which you will see probably when this notebook is made available. So here I import these Qiskit operators XYZ, which are Pauli operators, and the identity to define tight binding Hamiltonian. So in this first row, I define the XX terms, and in the second row, the YY term. Here we only use or define a 3 lattice side Hamiltonian, just for simplicity. That's why I only just expanded this in the sum here. So remember, these sums run over neighboring sides. So here we have the 0, 1 term, and here we have the 1, 2 term, okay? And the same for y. And then the z terms, I say, okay, we can have 3 different parameters for this epsilon, and each of these terms here has a different epsilon, okay? And then I sum them up to get the tight binding Hamiltonian. Then furthermore here I implement this exact unitary time evolution operator with this neat Qiskit functionality here. So essentially this is just the exponential of minus I to the t, the exponential of minus I times t times the Hamiltonian that I feed in here, okay? And then let's first look at the case where all of these epsilons are 0, okay? So we define our Hamiltonian, and we define an initial state. For this, I import these 0 and 1 states here and define my initial state like so, meaning that the initial state is the electron being on atom side 0, okay? So the occupation of 1 here means that the electron is on this side, and then occupation of 0 means that this side is unoccupied, okay? Then I define a time interval. So I say, let this evolve for until time 2.5 and do 50 time steps, okay? All right, so I do this evolution here, and I get an array of different states for each of these time slices, 1 state. And then what I want to measure is essentially the occupation of each side in this lattice, okay? So I say, okay, one possibility is that the electron is on side 1. Another possibility is on side 0, sorry, on side 0. Another possibility is that the electron is on side 1. And the third possibility is that it's on side 2, okay? Because there's 3 sides it can occupy. Okay, and so computing this this probability of the electron being on each side, I essentially loop over all of these side states here and compute the overlap with the state at each time step and square the absolute value of this overlap. Okay, so plotting this, I get the following graph. Here you see the probabilities for occupation of side 0, side 1, and side 2. And you see here this probability oscillates between 0 and 1, and so does this probability, and then the probability of the electron being in the middle, so on side 1 is also oscillating, although not as highly. But essentially you see the electron here moves from side to side and does not really care on which side it is, okay? Now, things change if we change our epsilons. So there's a phenomenon called Anderson localization, which is essentially if you have a random distribution of your epsilon. So if the energies that the electron needs to occupy a certain site are distributed uniformly within some range from minus W to W. Here I chose 3, minus 3 to 3. Then depending on these epsilons, you might get a different behavior of this material that you're modeling. So in this case here, the electron doesn't care which side it is on, and so it moves freely over this lattice, which is describing a conducting material, so to say, right? The electron just freely moves through the material. In this case, however, you see here, I randomly choose epsilon and I get these values, okay? Again, I do the exact time evolution of this and I plot or I compute and then plot the occupation of each site. You see suddenly the electron prefers to remain on site 0. Okay, so the probability of it being on site 0 is always between 1 and, or between 0.7 and 1, whereas the probabilities on being on the other sides is much lower. And so this is what we call localization. So the electron becomes localized on one side and it doesn't spread over multiple sites anymore. And this indicates an insulating material, right? Because suddenly the electron becomes localized on one side, doesn't move freely anymore, and so the material is not conducting or less conducting anymore. Okay. Right. So this is a very, very brief and probably also shallow intro into the physics of this tight binding model. But so let's do some dynamics using product formulas or an algorithm that I introduced before. So we use trotterization, and the reason why I wanted to show this model together with a product formula is not only is the physics interesting of this model, but also the Hamiltonian is the perfect example to show why product formulas are so strong, even though they have kind of the worst scaling in terms of gate cost of these decomposition methods. So the goal is to implement this unitary time evolution operator. With this Hamiltonian here, we have this unitary time evolution operator, right? And you see here that I split the tight binding Hamiltonian into, or the sum over these nearest neighbors into terms into these neighboring lattice side terms. So I have a Hamiltonian term or a hopping term for site 0, 1, and a hopping term for site 1 and 2, okay? And since we only have 3 sites, these are the only terms, and then we also have the Z term. Now, we cannot implement this directly in our hardware, okay, with our superconducting qubits. Instead, we need to make some kind of approximation like I showed you before to implement this in terms of 1 and 2 qubit gates. Okay, so we see that this H01 is not commuting with H12, and neither of those is commuting with HZ. Okay, you can check this for yourself, but let me tell you, it's like that. So we need to do a product formula or use a product formula to approximate this exponential. And we use the simplest case, the order 1 product formula, where we just say, okay, this is approximately the product of all of these exponentials individually. Okay. So then we do this and we note these are actually the only non-commuting terms in the tight binding Hamiltonian, since within this Hamiltonian, so within H01 or H12, these terms actually commute. So XX and YY commute with each other. And this is actually general. So if you have such a commutator with AA and BB, where A and B are both Pauli matrices, then this always commutes, okay? And so this means that each of these terms here, we can exactly decompose into these exponentials, which we now can implement efficiently in our quantum hardware, okay? So this down here is not an approximation, but it's exact because this XX commutes with this YY, okay? So we do the same for these terms here. And of course, all of the Z terms also commute because an operator always commutes with itself, and also they act on different qubits. Okay, so we do this, and we can use a neat Qiskit functionality to implement this operator. Namely, there's this Pauli evolution gate, which essentially we have to feed in a Hamiltonian or an operator, which is a sum of Pauli operators. So this has to be a sum of Pauli operators, a time t for which we want to simulate, and then a synthesis. And this synthesis, it's a weird name, but the synthesis essentially is the product formula that we want to use. Okay, so here we use Lee-Trotter, which you can import from this Qiskit module, which is a first order product formula, and then we have to specify the number of circuit layers that we want in this product formula. Okay. So we define a quantum circuit and this gate, which implements our trotter circuit, and then we append this gate to our quantum circuit and draw it down here. Sorry, this was kind of cut back here and then moved down there in the presentation. But yeah, essentially we get an implementation of this entire exponential, which is then, if we were to compile it to our basis gates, would be split up approximately in the fashion of product formulas. So we do this simulation using this Pauli evolution gate to implement a product formula. We'll do this for an order 1 and an order 2 product formula, okay? So here, very basic simulation. We essentially have steps, time steps, so 50 time steps. And so at each time step, we say, okay, we take the time at that time step, and then the number of layers that we want is the number of time steps that we have done so far, okay? So at every time step, we increase the number of circuit layers here by 1, okay? Then we transpile it into our basis gates. Here, ID, RZ, SX, X, and CX are the basis gates that are native in our hardware, but this is, for instance, a C0, this is an RZ rotation, and so on. And we do this simply to count the number of C0 gates that this circuit has. Okay, so I want to show you the scaling of the number of C0 gates, which is the most expensive gate that we have in our hardware, to show you to compare with the product formula of order 2 later. Okay. Right, so we do this, and again we compute the probabilities at each site. You see it's the same evolution as before, so this approximation seemed to have worked very nicely. I do the same thing with order 2 product formula. Now the synthesis is a different one, namely Suzuki Trotter, which is the synthesis for any higher order product formula. And I specify here that I want an order 2, okay? I can also do order 4 and so on. And again, I append 1 circuit layer at each time step, okay? So then next I compute the infidelities. So I compute the overlap, or 1 minus the overlap with the exact state at each time step to get a metric for the error that I do in both of these simulations. So for product formulas, order 1 and order 2. And then I plot these things. So on the left here, you see this infidelity, so the accuracy of this product formula order 1 and order 2 simulation, where you see here product formula 1, where order 1 is much worse than order 2. So the lower here means that the error is closer to 0, which we want. So product formula order 2 is much better here. But you also see that the gate count, so the number of C0 gates, is much higher in the case of product formulas of order 2, okay? So, okay, this for now doesn't look like anything special. You have better accuracy, but you pay for this accuracy with more gates, okay? So, yeah, nothing surprising. The fact that it's like this is because we naively just appended one circuit layer in this product formula at each time step. So we can be a bit smarter about it, which I'll show you now. And essentially, so of course we could not do this in a real simulation, but if we want to compare order 2 and order 1 product formulas, we can compute the error at each time step and say, okay, I want an accuracy of 10 to the minus 2 in the end, an error of minus 10 to the minus 2. And every time that my simulation with the product formula drops, or does a higher error than this threshold that I define, I append one circuit layer until the error is lower again, okay? So here I do this and I say, okay, I want at least 10 to the minus 2 in fidelity. I computed it at every time step. And then if my infidelity is below my threshold, everything is fine and I go to the next step. If it's above my threshold, so if the error is suddenly higher than what I want, I say, okay, increase the circuit depth by 1 and then go back and do the same. Okay, so you see here I start with a depth 1 circuit. It's fine for the first 4 time steps. Suddenly the infidelity is higher than 10 to the minus 2. And so I increase depth to depth 2. Okay, and then it's fine again for some time steps, and then it increases again, and I increase the depth again. Okay, so all of this is just to show basically the resource requirements of order 1 and order 2 at the same accuracy, okay, not at different accuracies like we do here. Okay, so I do the same. This is for order 1. I do the same for order 2. Again, compute the infidelities and the gate counts. And what I end up with is this. So here I show the infidelity of order 1 and order 2 product formulas, simulating this tight binding Hamiltonian, requiring that they always remain below 10 to the minus 2, okay? So now you see they're roughly the same. And now you also see that actually an order 2 product formula requires much less 2-qubit gates than an order 1 product formula at the same accuracy, okay? And this is the take-home message. So be careful what you compare, and be careful that you always compare different algorithms on the same footing, okay? Right, so I hope this was an insightful lecture for you. And with this, I will finish. Thanks very much for listening.